Okay, the last thing that we're going to look at in chapter 6 is modeling data. Now, there's three things that we're going to be looking for when you describe data. Three things that we have here are the direction, the form, and the strength. When I refer to the direction, I'm talking about positive and negative. So thinking slope. Does the data look like it would have a positive slope, or does the data look like it has a negative slope? So in describing, it'll be one of those two. The next we'll look at is the form. There are two different types of forms that we're concerned about. Either linear, does it look like it would be slope-intercept form? Or is it anything else, nonlinear? I'm not going to ask you to do quadratic, exponential, or anything like that. It's either linear or nonlinear. And there are some examples. And the third and final thing will be the strength. Are all the data points really, really close and compact together? Would it make a strong correlation? Or is there a correlation, but the data points are kind of spread out to give you a weak? Or are the data points so spread out that you just possibly can't see any correlation to give you no correlation? Those are the three things, and we'll go in those orders with the direction, the form, and the strength. So this table shows the cost of smartphones in different years, the graph, and we're going to graph this data on the paper here, on the graph that I provided, and we're going to describe its direction, the form, and the strength. Now, I'm going to change the values on the x-axis to years since 2012. So 0 is actually going to represent 2012. 1 is going to represent 2013, and so on. So in 2012, it was $325.50, and I plot all the rest of these all the way up to 2016 to give you $794.69. Now you see the data. So we'll start with the direction. Now, if you look at the direction from left to right, it is going up. So that means that we have a positive direction. Form. Now, I use kind of this idea of a line of best fit to see would it possibly be linear or could it possibly be nonlinear. Now, those dots are extremely close to the line that I drew there, so that suggests that it is nonlinear. And also, with the dots being that close to the line, that also suggests that it has a strong strength. So whenever we go in and describe it, it has a positive direction, the form is linear, and the strength is strong. Another thing that we're going to look at in this particular section, just one little formula, it's called the change in the base formula. Since last section we talked about logarithms and the common log. And this is basically around the calculator. If I have log base b of x and I want to use my calculator, the way I have to type this in is I got to do log of x divided by log of b. Now notice that where the x is and where the b is from there. So the big number in the log is what I put on top. The base is what I'm going to take the log of on the bottom. Now the reason why this works is because when you type log of b into the calculator, you are telling it to do log base 10. Now our number system is base 10, so that's why we have a common log of base 10. There are some calculators that do allow you to put in the base. If you have one of those, that's great. If not, this is how you'll have to use it. So let's apply this. 1991, the internet was introduced and the first computer virus threatened should be 500,000 computers. Computer engineers calculated that one person's computer could have infected 5 other computers every minute. They created an exponential function to calculate how long it would take this virus to spread to 500,000 computers. How many minutes would it take for this computer virus to destroy 500,000 computers? Well, the exponential function that they came up with was 500,000 equals 5 to the x power. Now, since my exponent is a variable, I can convert this to logarithmic form. So drop my base, bring the answer over. The exponent now goes to the opposite side, and now it's in logarithmic form. Now, I want to type this into my calculator, but I can't do this because it's programmed to do log base 10. Here's where the change in base formula comes in handy. The log of 500,000 is going to go on top, and on the bottom I'm going to put log of 5. Now each of those are numbers, so I can convert those to a decimal type of number. So I can type in log of 500,000 and get a rough estimate of 5.7. On the bottom, I can type in log of 5 and hit equals. And again, I'm rounding, but it's somewhere close to 0.7. So I've got a number that I can just divide 5.7 divided by 0.7, and it'll be approximately 8.15 minutes. So it would only take about just a little over 8 minutes to infect 5,000 computers with this computer virus. That shows you how fast things can spread.